today we'll talk about Fluitec and more precise this inline reaction technology. A bigger system, they're based on components, as I recently mentioned, that we looked at yesterday. And today we will introduce you to the functionality and the application of the Fluitec inline reaction technologies during this session. My name is Alfred Berglund. I work at a company named Turne. I work as a product sales manager, soon to be 2 years. And my spokesperson today is the man, the myth, the legend himself, Alain Georg, who is the founder of Fluitec. And today he works as the head of R&D at Fluitec. This is also your contact from Turne. So depending on where you're located around in the world, you have different persons who have different areas. So me, for example, Alfred Berglund, I have the district Sweden and Norway. If we go to Finland, if you're located in Finland, we have a person named Olli-Pekka, who you should be in touch with. If it's Denmark you're located in, we'll talk to a person named Rafi. If it's the Baltic states, then you will be talking to Andris. And if you're in Poland, you will speak to the Rod. Please make sure to follow us on our social media. We have a Facebook account, we have a LinkedIn account, and we also have a YouTube channel. On Facebook, we post a lot of interesting news articles. Same on LinkedIn as well. We share articles from our suppliers, news from our suppliers, news from Turne within the company. Events like this one, for example. So you can tune in and also just get in touch with us. If you need something, you want to get in touch, this is a good way of doing it. We also have a YouTube channel. We will upload part of the webinars we're having at Turne, among many other short videos. If you want to share it with your colleagues, go back and look again, see if it was interesting enough for you. Please do that. And without any further ado, I think we should begin. We should begin with the main presentation. So I will hand over the podium to Alain from Fluitec, and he will.
My focus today is to talk about continuous reaction calorimeters for studies, screening and process development and process safety. Just let's have an overview about our products, what we're going to talk. First of all, I'm going to talk about reaction technology generally. I describe a little bit the functional work of the reaction calorimeter, what is the value of reaction calorimeter, shortly show you about the rapid screening, the reproducibility of reaction control, and some analysis and some examples. So let's start. Here you see an overview of the Fluitec products. So we divide, we have 4 divisions in our company. We have on one side, on the left side, the static mixers, which and the mixer heat exchangers on the right side. These are the products where Tobias was talking yesterday. I am going to talk today about the inline reaction technology and just some applications about the systems. Okay. About 13 years ago, there was a European project which was called F3 Factory. And in this European project of, let's say, about a volume of 30 to 40 million euro, one of the target was to develop laboratory equipment which is able to scale. The target here was to develop milli-reactors and not micro-reactors, because mostly micro-reactors, they have an advantage that they cannot be scaled. So the result of this research project was the ContiPlant equipment, like you can see here, and we divide the ContiPlant equipment into 3 parts. One is the ContiPlant lab, which is an equipment which can be handled in a fume hood. Then we have ContiPlant pilots. This can be pilot plants, but it can be also weigh-in fume hoods, which are used. And finally, we have the ContiPlant modules. These are assemblies, these are products, can be different products on which are scaled. Just have a look to the ContiPlant. The ContiPlant is a plug and play equipment. So you just have a housing, a double jacketed mixer, heat exchanger, and on each head you have 4 connections. So you can install pressure measurements, you can install injection valves, you can install temperature sensors, bursting disc, NIR, Raman equipment. All these things can be installed in this reactor. Here you see a cut, so here you see 3 reactors connected together. The housing is insulated as a standard, and then you see the double jacketed, the static mixers. We have different size, different types, different geometries. We can even run the reactor without static mixers. We can fill it with some, for example, with a trickle bed. We can use it as a distillation column. We can even use it as a rectification column. Can be also used finally for crystallization. So it's a wide plug and play system. So this is a custom-made result. So when clients has a specific application, then we do a pre-engineering. We are focused on the needs which are required, and then there will be some results. Here you see this is a rack which is for a walk-in fume hood. It was for a mass polymerization. This here is a rack which was used for radical polymerization, and the client, they had problem in the beginning with fouling. So what they did in the first part of the static mixer, there was a redundant system. So you could run the reactor in the first part on one side, and when you got some fouling effects, you started to clean the reactor and you switched to the other reactor. So that's why we call it a redundant system. Here you can see a ContiPlant equipment, which is a reactor, residence time reactor, premixer, and finally also a small distillation. So you can see this equipment can be used as plug and play equipment, and yeah, from these products, there will be finally a scale up. And how does such scale ups looks like? You can see it here. This is a typical small production plant with about a flow rate of, let's say, 100 kg per hour. It's a high pressure mass polymerization reactor. Here you see the result, the final result of a very big reactor type. This is for a flow rate of about 7,000 to 8,000 kg per hour. So this is a typical result, and we call that a partus assembly. That could be also a result when you are when you use a ContiPlant equipment and you do the scale up. It can be also just an individual mixer or a heat exchanger, which could be the result for the need of the client. Here you see a picture of a bigger heat exchanger, and here you see the mixing elements of a quite big residence time reactor. An additional result could be also assemblies with safety concept. These are assemblies where we also are focused on the dosing systems. We have a safety concept, we do a HACCP, everything is already done. We have a programmed control system, so clients can just take all this knowledge and he can reduce the time to market almost, due to our experience, it's almost a year. And that means you can reduce quite dramatically the cost. So I repeat, so we have assemblies where we can say it is a partus assemblies, a couple of reactors connected together. It can be just a reactor, a static mixer, mixer heat exchanger as a result, or as you see here, finally, the assemblies for the safety concept. So, but what we found out the last 10 years was sometimes we really had problem in scaling up a reaction. Not due to the fact we have standard equipments, they work quite good, but sometimes client had really problem because he didn't know so much about the reaction. He had some results from a RC1, from a classical batch reaction calorimeter, but he didn't have some information about what happened exactly in this reaction, how fast is this reaction, and he wanted to know a little bit more about the kinetics. He had a polytrope temperature profile, but nobody was able to look into the reactor. So they just connected, quite typical like with the micro reactors. They run it, inlet, outlet, they measured good quality, and then they want to make the scale up. And that's not always possible. So here I just have a comparison between a batch reactor and a continuous calorimeter. Mostly batch or feed batch reactors, calorimeters, they are run almost isothermal. No reaction is isothermal, but we can say almost. It can be used as a flow and a heat balance calorimeter. You have specific reactions that can be measured. The adiabatic temperature rise can be calculated. Specific heat capacity can be measured. But you have some problems in transfer these results into a continuous production. So there is sometimes some result missing. Another thing is you have to calibrate a classical batch reactor, and the screening of such a system takes a lot of time. If you compare to a continuous calorimeter, we are running the system in a polytrope temperature profile. It can be used as the heat flow and the heat balance calorimeter. The specific heat of the reaction can be measured. The adiabatic temperature rise even can be calculated, but this is nothing special. But what we do need here is we need the specific heat capacity and the viscosity and the thermal conductivity of the liquid. So this is a basic which is really important, and that's also why we can support you in measuring this equipment, because we have certain measurement to do that. What we can do is we can transfer to a continuous production. It's quite safe. The calorimeter must not mandatory calibrated. And the screening of such a reaction can be very, very fast done. So this is the benefit. Something which is probably always also quite important is the flexibility of such a reaction calorimeter. Mostly the reaction calorimeter or the reactor himself is quite flexible, but there might be sometimes some challenges in the point of view of the dosing equipment. So let's have a look how we have solved that. Here you can see a classical standard reaction calorimeter, which is fully automatical working. You have two dosing systems, some vessels. Then you add the liquid into the reaction calorimeter. This is the key product. And then you sample, and a heating cooling equipment is needed too. The same is available. You can have a look here. This is a Hastelloy reactor with peak dosing systems for, let's say, quite corrosive liquids. And this reaction is a low-cost manual reaction calorimeter, which can be used handable. So you are just putting on the pump the flow rate, you run the systems, and you can measure the temperature profile. So you note the numbers and you analyze it by a simple software. How does such a system work? This is the PNID that you can have a look. We have these feed tanks. We also always use a solvent tank because we want immediately clean the system after a screening. We have the pumps, we have pressure measurement, we have the flow rates, the temperatures, and the key of our product is these axial temperature sensors. Of course, we also have the heating cooling equipment. We can use a flow meter, but, and this is unique on this system, the heat balance doesn't work on the heat balance of the heat transfer media, because this normally never works. And I think since about more than 30 years, people are trying to realize a continuous reaction calorimeter which is working, but they always were struggling with the heat balance on the heat transfer side. Let's have a look to the key technology. Okay, what we have is a temperature sensor. It's a capillary of a diameter 1.6 millimeters, so very, very small, very compact. And we just install this capillary in the center of the static mixer. Now, sometimes people ask, yeah, I don't want to have a reaction calorimeter just for static mixers, and this is not the point. This is not the key. The static mixer has more jobs to do in the reaction calorimeter. One thing, of course, is a premixing, but that can be done in another way. And another thing is he has to create a residence time distribution. So that means the residence time distribution of the reactor has to be very narrow. And finally, the measurement of the temperature sensors. And what we have found out in the last 10 years, that these temperature sensors are very, very accurate. So we can measure temperature in plus minus 0.2, 0.5 degrees C. And this is for a pilot plant with a flow of 5 to 10 milliliters per hour. So means laminar flow, very accurate. Here you see a view. So along the reaction, we are measuring the temperature. And this is a quite interesting thing. Here you see an analyze. What we are doing is we call it a segmental analysis. So this is the software which is calculating in 1000 steps along the reactor. He's doing a heat balance, a special heat balance, and we are able to calculate, for example, the K value and the heat, the thermal heat in the system quite in a good way. So we call it the segmental analysis. We did also quite a lot of research on the mixing time, because mixing time is always an issue. It has an impact on the reaction. I will show that later on. The way how we did it the last couple of years was always with decolorization reactions, and we have a good knowledge in calculating the mixing time, the homogeneity, the micro and the micro maxi, the micro and the mixing, the macro and the micro mixing. I'm sorry. Okay, now when people are talking about functionality, flexibility, and the continuous reaction calorimeter, that might be an issue. So what we did is we realized something like a morphological box where we divide the functional steps to have a look what we need. So here you see you have, for example, different liquids, a gas, a crystallized liquid, a high viscous liquid, low viscous liquid in low temperature, or a high temperature, or just a normal low viscous liquid. You need a storage tank. You need a dosing technology, you need a preheating, sometimes yes, sometimes not, and you need the reaction calorimeter, and finally you need to control the temperature of the system. So the strategy of this modular technology is quite important, because we want that our clients, they have a flexibility, they can act quite fast, and sometimes it is the point, some dosing system doesn't really work. They have to choose something else due to corrosion, due to the viscosity, due to any kind of thing. And the strategy of Fluitec is that we are going to sell a basic equipment, and this basic equipment can handle, I would say, 80 up to 90% of all the reactions which are needed. It's a little bit divided in a fully automatic system, it's divided in a manual system, or it is divided in API pharmaceutical low temperature application. So this is the three basics that we have. And then we have some additional equipment. And these equipment are on stock at Fluitec and can be rented. This is an overview. Again, you see the morphologic box. You see storage tank, dosing technology, and sometimes you have to take care to each step, and we analyze that together with the client. Even it can be in ATEX, explosion proofed. So in this way, we can really build the plant, the custom-made plant, and this is the basic of the modularity. So let's go back to the reaction calorimeter. Why did we develop this equipment? We had clients, they couldn't really scale it up, not due to the fact that the surface to volume ratio was not okay, not to the fact that the heat transfer was not okay. No, the fact was the kinetic. And sometimes it was quite difficult to analyze the kinetic, and kinetic is something quite important for the scaling, but also for the process safety. And here you see the four possibilities or the four values which are good for the reaction calorimeter. So we can do a rapid screening, we can do a continuous process scaling, we can make process safety and support. So what does that mean? A rapid screening, what is this? A rapid screening is you prepare the reaction that you want to run, you have the liquids, you prepare the reaction calorimeter dosing systems, and then and one day you do the rapid screening. So that means quite simple. You run a reaction with different flow rates, with different temperatures, and then you analyze the temperature profiles that you get along the static mixer. So if you increase the temperature, then the profile will be a little bit higher. If you reduce the temperature, then the temperature profile will be a little bit lower. If you increase the flow rate, then the reaction can be also a little bit earlier or later, depending on the kinetic. So if you do such an analysis in one morning, you will be able to get all the informations based on safety and based on the scale up. How does that work? The fully automatic reaction calorimeter is fully automatically running. You have a computer, you are running the systems, you run the system with a certain flow, and then if you see, okay, I have a stable flow, then you just put the button on the computer, and the computer will immediately store all the information in the computer with the analysis. And after that, you get even the informations about the heat transfer coefficients and all these informations that you need. This is important, and it is important why you can increase the development time. This is a key point because time to market is very important. If you got this information and you analyze them, then you are focused on the heat transfer, the specific heat transfer capacity of the systems. As you can see here, this is a classical diagram where you compare the mixer heat exchanger, with Tobias has shown yesterday. You can see here that the heat transfer capacity is quite high on a Fluitec mixer heat exchanger, and this is the key value for the scale up. So the program or the results which you get in the screening, they just give you an information, and they say, okay, I need a specific heat transfer capacity of, let's say, 500 kilowatt per cubic meter per Kelvin. And that means your continuous reactor can have a volume of 1 liter for 1 meter, that he can handle that. And if you say, okay, I can risk a temperature profile of 20 degrees C, the program will automatically calculate the specific heat transfer coefficient for a polytrope profile of a maximum temperature increase of 20 degrees C. Another thing which is also interesting is that if you invest into a reaction calorimeter, you already have the control system. And you already have the control system for the scale up, because we decided that we are using industrial equipment also for the reaction calorimeter and no lab equipment. So control system is programmed. Of course, you will have a risk analysis, you will have a hazard study, an FM analysis, and you have also will have the concept of an inherently safe continuous flow reactor. This is also a key point which speeds up the time to market really extremely and reduces the costs dramatically. Then the process support. Okay, after such a screening, we can talk with the client. We are making analysis, and we developed this diagram, which you can see here. So we just have a look to the specific heat of the reaction, and we do some analysis on temperature, for example, on the T onset temperature, or also from, we compare measurements from the RC1. Okay, let's have a look what such a reactor is able to do. Here you see the rapid screening. So we have a reaction with a specific heat of 210 kg per kilogram. That means this is about a adiabatic temperature rise of 114 degrees. The T onset is 74 degrees C. So what is the T onset? Or that is a measurement which will be done, or which also has been done in a DSC calorimeter, and he gives the information if you get some side reactions, if you get some runaway scenarios, and here this blue line is, for example, in this reaction, the T onset. Here the decomposition of the reaction starts. This red line here is the measurement in a feed batch reaction in an RC1 reaction calorimeter. So you do this screening, and we will especially have a look to the temperature peak, so to the highest temperature point, because this is going to be a critical temperature which could lead decomposition, for example. After the screening, we analyze it. We have this diagram, and you can see here, these are the red temperatures, the red points. These is the reaction control at low temperature, and then the decomposition here. I just cannot see it. I have to put it away. Okay, here the decomposition at the T onset temperature is in this application about at 74 degrees C. So this might be here. So you see, we run the reaction over the T onset. So it would be a decomposition, but it wasn't. And that was surprising, not for us, but a lot of batch specialists, they have been surprised that you go over the T onset from a DSC measurement. And you can see here when we run the system under the T onset, or just at the maximum on the T onset, the specific heat was totally similar to the reaction calorimeter, to the batch reaction calorimeter. And if we go over the T onset, then we will start some side reaction. We will not start to complete decomposition, but we will start some side reaction, and they will be measured in the specific heat of reaction. Okay, this is another measurement. This is a much more dangerous reaction, has a temperature rise of 202 degrees C, and a very critical decomposition of additional 350 degrees C. The T onset is in between 118 for one feed product and 128 for the mixture. It has also a certain viscosity ratio, and we were measuring here on different flow rates and on different temperature profiles. So this is something, this diagram that you see here is interesting because you see, oh, okay, I have this temperature profile, and this might be, okay, perhaps almost continuous, almost a complete conversion, but probably not all. Here you can see this is not, the reaction has not finished yet. You can see that all the temperatures were running under the decomposition. So we do not expect any side reactions or decomposition reactions. And what we did is here the red point. This is the specific, the red points. This is the specific heat of the reaction that we got here. As you can see on the curve, not 100% conversion was realized. What you can see here, when you take the sample and you measure the conversion and the different, you add the difference of the heat, then you will see, okay, we are quite close to the specific heat of the reaction on a RC1. This is an interesting picture of a reaction. You see, we wanted to know about the reproducibility of these reaction systems. Can we reproduce the reaction, same flow rate, same temperature? We were running the temperature, so the exothermy was working quite good. But here we just saw something, and this is quite interesting. We call it the shoulder. It's a shoulder because normally a reaction should go down, and then you see, okay, we have 100% of conversion, everything is good. But here we had these two deviations, and that was quite interesting. So let's have a look. What does it mean? At 74 degrees here starts the decomposition or the side reaction. And this is what happened here. We can see, oh, there is some side reaction starting. And here, depending on the way the reaction acts, you have some small deviations. You can see here, that was the measurement of the reaction, the two here. And here you see we were producing some more heat compared to the measurement of the RC1. So it's clear we want to reduce these effects, and sometimes the mixing time on the reaction calorimeter is too long, and there can be an impact on a reaction when you have a too slow flow, or the mixing time is too low. So that's why we can also implement a premixer to make a premixing effect. And let's have a look, what does it mean on the temperature profile. You see two measurements without premixer. And the blue line is a measurement with a premixer. You see that reaction starts faster, earlier. It's generally a slowly starting reaction, but due to the better mixing, the reaction starts a little bit faster, and you have the profile here. So what does that mean in the analysis of our diagram? You see all three temperatures are below T onset, so we do not expect any side reactions. These are the two curves, the orange and the brown one. So we have a specific heat. We know we have not full conversion. This is really good seen that the diagram or the peak is very at the end of the reactor. So we need more residence time. This is quite easy to realize because we just plot and play with a second reactor. This here, what you can see here is the result of the premixer. And you see, still we do not have full conversion, but we have more conversion to the premixing. This is another picture. Here we wanted to realize a system, or we wanted to realize a runaway scenario. So we were running the reaction at 90 degrees C, so almost 40 degrees over the normal temperature of where we were running the reaction. And the peak was going up to 217 degrees C, so quite high, but we didn't have a decomposition. Here you see we were in all three reactions we were running over the T onset. This is the peak, the green peak, which is quite high, and here you see the heat of reaction. When you go over the T onset, you will create start side reaction. But what is really surprising in a continuous mixer heat exchanger, we almost cannot realize a runaway. And this is very promising. As you know, when we have a look to the safety, first of all, not all reactions are dangerous. So we have different classes of reactions. So we divided the reactions in different classes. So here we use the classical knowledge from Professor Stössel. This is the Professor Stössel diagram where we divide the reaction in different classes to define, okay, what do we need? Okay, is it okay if we just run a passive, inherently safe system, or do we need a passive and an active, inherently safe system? Okay, we said we do not have a runaway scenario right now. Well, this is something which we need to take care quite a lot in the future. And that's also why we started with the University of Zurich an InnoSwiss project to find out what is the impact, what is the influence on these high peaks. Is it due to the fact that the time, the thermal stress that we have on the liquid is just a short time to do the peak? And is this the reason why we do not have any decomposition, or what kind of other reasons they can be? But anyway, we need a safety concept. And we divide it in 3 steps. So we say we have an operating device. So our control system is running without with the classical technology that is known. But we also implement an event preventing protective device. And as you see the results of the measurement that I've shown here, it will be clear that we need to prevent a continuous flow reactor against the total failure. Power failure, total failure, these are the dangerous systems. Against this, we need to have something. Finally, we also have a damage limiting protective device. So this can be bursting disc, safety valves. So it's a whole complex system. So we need some additional equipment. We need additional measurements and additional safety. And one really important thing is, if ever somebody is going to tell you, well, continuous processes are less dangerous because the volume of the reactor is so small. Yes, it's true, but it is also not true. Because if you would have a decomposition in your reactor or a deflagration in your reactor, it will run through your pipings into the tank, and then you will have the same disaster. So what you need is a deflagration protector, and we invent this technology. We realize some deflagration protector which can handle runaway scenarios in different ways, just thermal runaways based on gas, thermal runaway based on pressure and steam. And what is the key technology of Fluitec, of the continuous reactor, to handle a continuous reaction quite safe? We call it, this is the Fluitec Safety Purge System. So as you have realized now, is that when we have a total failure or a power failure, then we will really have a dangerous system. A runaway scenario is a no-go. We will never have it and we want never to have it. The axial sensors in the reactor, they can control the temperature profile. They really handle that in a good way. And if there is some deviation, which is very good controllable with our control system, which you already have from the ContiPlant lab equipment, from the reaction calorimeter, you can just start the safety purge. And this is a counter current purging. So if we have some deviation in our reactor, we purge our reactor immediately to create a safe situation. And this looks like this. So you have two dosing systems. You have the equipment. Here inside is the reactor installed. Continuous flow reactor is the outlet. And here are the safety valves. And if we have a dangerous situation, we immediately purge the system. And for a low viscous liquid, it takes about 5 to 10 seconds to purge the whole reactor. But during purging, we increase heat transfer coefficient so much that there is no possibility of a thermal runaway. So what we use, we push the critical liquid into the quench. And here in the quench, we have already some mixing technology, some static mixing technology, which is handle and inactivating the liquid immediately. After that, you just can handle the technology like in a batch. Okay, that was an overview of the reaction calorimeter. You see that this was really a need, which we found out after the ContiPlant reaction, after the development of the ContiPlant reactor, that we really need an additional equipment. And this equipment will change the flow chemistry in the next 10 years.
Thank you very much, Alain. It's some heavy stuff, heavy stuff to look at. But I'm very impressed with the scale-up concept you have, because it hits very wide on the market. A lot of people can use it more than they probably think with this type of reactions. And I was also very impressed with the calorimeter and continuous calorimeter. It's very unique, I say. So I want to thank you very much, everyone, for joining, and I wish you a pleasant day. Thank you.